Hello everyone, so this is free response problem 2021 AP Chemistry number 3. This problem is asking students about important lab skills. Two different methods are used to determine the concentration of a given chemical species, which is gravimetric method and spectroscopic method. Let's read the problem. A student is given the task of determining the molar concentration of a copper-2 sulfate solution using two different procedures, precipitation and spectroscopy. Copper-2 solution, we want to determine the concentration of copper-2 sulfate solution. We know what it is, but the concentration is unknown, and two different methods can be used to determine the concentration. Let's look each method in detail. First method is precipitation method. For the precipitation experiment, the student adds 20 milliliters of 0.2 molar barium nitrate solution to 50 milliliters of the copper-2 sulfate solution. The reaction goes to completion and a white precipitate forms. So this one is a precipitation reaction on insoluble solid precipitate. Here the color is white, is formed. The student filters the precipitate and dries it overnight. The data are given in the following table. In this data, let's look at the mass of dry filter paper and mass of filter paper and dried precipitate. So initially, in order to filter out the solid precipitate, we need to use a filter paper in a filtration setup. The mass is 0.764 grams initially. When you do filtration, when you perform the filtration and dry out the precipitate, the mass of filter paper and dried precipitate is 1.136 grams. So let's calculate the difference, which gives us the mass of dried precipitate. This value is needed for the calculation. The mass of the precipitate and mole number of precipitate, finally, mole number of the reactant calcium sulfate, copper-2 sulfate. So the mass is 0.372 grams. Let's have a brief review about solubility. In general chemistry, we are interested in aqueous solutions only. When you go to college and take organic chemistry classes, you'll learn many reactions, many solutions occurring in organic solvents such as benzene or hexane or dimethyl sulfoxide, those like solvents. But in general chemistry level, we are focusing only in water. Water is an excellent solvent, very polar solvent, and many ionic compounds are dissolved in water well. So let's look at this solubility rule. Left-hand side is generally soluble ionic compound. The right-hand side of the table is generally insoluble ionic compound. We usually look at the anion portion of an ionic compound. Let's look at it. Left-hand side, soluble ionic compound. So when the ionic compound contains ammonium ion or group 1A alkali metal cations, sodium ion or potassium ion, generally the ionic compound is soluble, no exceptions. And from this point on, we'll be looking at only the anions. Nitrate ion, all the nitrate ion compounds are soluble. Halide, chloride, bromide, iodide, they are generally soluble, but there are some exceptions. When the compound contains silver ion or lead-2 plus cation, it becomes insoluble, such as silver chloride, silver bromide, silver iodide, lead chloride, lead-2 chloride, lead-2 bromide, lead-2 iodide. Finally, we are interested in sulfate. So I color this column. Sulfate, when the ionic compound contains sulfate and ion, they are generally soluble, but there are three exceptions. When this sulfate ion is paired with alkaline earth metal cations, such as calcium 2 plus cation, barium 2 plus cations, or lead 2 plus cations, it becomes insoluble. So I wrote the formula below the table: calcium sulfate, barium sulfate, and lead 2 sulfate. They are all insoluble in aqueous solution. Here in the problem, initially we have dissolved copper 2 sulfate solution in water. So copper 2 sulfate is soluble. Now let's look at to the right hand side of the table. The hydroxide ion, the compound contains hydroxide ion, is generally insoluble, except sodium hydroxide, potassium hydroxide, ammonium hydroxide, or calcium hydroxide. Sodium hydroxide and potassium hydroxide are very often used in chemistry laboratory to prepare strongly basic solution. And calcium hydroxide is the solubility is limited, but we treat this one as a soluble ionic compound. Finally, sulfide ion, carbonate, and phosphate ion. And when an ionic compound contains these ions, they are generally insoluble. Exception is sodium ion. This one combination with alkali metal cations, sodium or potassium ion or ammonium ion. So understanding of this solubility guideline is important. Okay, so I just said a reminder of this one. So let's look at the schematic representation of the reaction. First, we have copper 2 sulfate solution, which is a blue solution. And when you treat this one with the barium nitrate solution, we have a blue precipitate. I mean, not blue precipitate. Let me correct myself. We have a precipitate. So I will precipitate the representation of a test tube, and we need to filter this one. So we are using vacuum filtration. The setup is called Buchanan funnel. And after the filtration is over, we need to dry the sample, because currently in the filter paper, on the filter paper, the sample is wet. So many times you're using drying the sample in the oven, or in this case, in this problem, it doesn't mention about the oven. So we are assuming that the sample is dried in a drawer of the laboratory. Now let's write the balanced net ionic equations. Many times we are interested in what is happening in net for this precipitation reaction. Precipitation reaction is one kind of double replacement reactions. Let's write the skeletal equation first. Copper 2 sulfate and barium nitrate, these two solutions are mixed. And we know that these are all soluble ionic compounds. So what they are present actually in solution is copper 2 plus cation sulfate anion, barium 2 plus and nitrate anion. So let's make a double replacement reaction. Then barium 2 plus, and let's remind ourselves about the general rule. Same charges repel each other, different charges attract. So let's make a double replacement. Barium 2 plus and sulfate ion, they are pairing, forming barium sulfate. And look at the solubility of barium sulfate. They are insoluble, so let's write it out as solid. Here I wrote it as solid because it is insoluble. So now the result of this double replacement is copper 2 nitrate. Copper 2 nitrate is soluble, so I wrote it as aqueous because it contains nitrate. Remember that nitrate compound is all soluble. So let's make a molecular equation. So we have two products, and when you consider the number of atoms and balance it is 1:1 and 1:1 ratio. And in order to write net ionic equation, focusing on the change of the phase. So initially they are all soluble. It has changed to this solid precipitate. So focusing on this solid and going backward. In order to form barium sulfate, we need to have barium ion and sulfate ion. So that's how we write this equation. Barium 2 plus cation from the barium nitrate solution and sulfate ion from copper sulfate solution. They are sticking with each other strongly to form this insoluble ionic compound barium sulfate. So we have the remaining two ions, copper 2 plus and nitrate ion. They are not participating in this reaction. So we call this one spectator ions. Once you determine the net ion equation, let's move on to find out mole number of the precipitate. So we determine the mass of dried precipitate from the data, the table, and 0.372 grams of barium sulfate. And when you add up barium and sulfur and oxygen all together, we find molar mass is 233.38 grams per mole. So let's set up a conversion factor. 1 mole of barium sulfate has 233.38 grams of mass. Then let's get started from this given mass, calculated mass of barium sulfate, and multiply this conversion factor. Then we have 0.59 millimoles of the value. So the mass of the mole number of barium sulfate formed, the precipitate formed is 0.159 millimoles. And calculate the molarity of the original copper sulfate solution. So this one requires a series of thought. We need to think about how to calculate the molarity. So first, molarity is a very important unit of concentration. We know in kinetics and thermodynamics, we are using molarity to write the formula and equation. And molarity is defined as mole number of the solute per the volume of the solution. So let's write the molecular equation again. Copper sulfate, copper 2 sulfate and barium nitrate. They are mixed and forming copper 2 nitrate and barium sulfate, the solid precipitate. Let's write the amount. So copper 2 sulfate, the molarity is unknown. We have used 50.0 milliliters, and barium nitrate, the concentration and volume, both of them given. And as a result, by this method, by this gravimetric method, we were able to determine the barium sulfate, the mole number is 1.59 millimoles. Then let's calculate the mole number of barium nitrate. The molarity times mole number, molarity times the volume gives us the mole number. In this case, 4.0 millimoles. Here, milli, mole per liter and milliliters cancels out. Liter and liter cancels out. Milli is simply number prefix. So milli is remaining. It is combining with mole. So it is 4.0 millimoles. So I have typo. I need to add milli there. The amount of barium nitrate is in the solution is 4.0 millimoles. And this is an excess reagent. Let's think about it. So let's assume that if barium nitrate is a limiting reagent, then because it is 1:1 ratio, all the coefficient is 1:1, then it would produce 4.00 millimoles. Here again, millimoles of barium sulfate. But actually, we measured out and the calculated amount of barium sulfate formed is 1.59 millimoles. So it is much less than half of the amount of barium nitrate. So clearly this indicates that, it shows that barium nitrate is an excess reagent. Then calcium sulfate is a limiting reagent. So we need to show this one to receive a full credit. We have a 2 reagent. We need to show, we first determine which is a limiting reagent. Once we determine calcium sulfate is a limiting reagent, then barium sulfate, this one is coming from the copper sulfate. So 1.59 millimoles of barium sulfate, let's go reverse. And it is 1:1 mole ratio. So then copper 2 sulfate must be also the same mole number. Now, molarity of copper 2 sulfate is mole number divided by the volume. Here, the volume of copper 2 sulfate was 50.0 milliliters. So 1.59 millimole divided by 50.0 milliliters is given 3.18 times 10 to the negative 2, or 0.0318 millimoles per milliliter. Here, milli is simply number prefix signifying 1/1000. So we cancel out milli, and final concentration, final unit is mole number divided by liter, which is molarity. Now we finish this method. gravimetric method. Let's move on to spectroscopic method. For the spectrophotometry experiment, the student first makes a standard curve. And this is what we need to do. Spectroscopic method is widely used in all chemistry labs. And for my research career of 20 years, I've used this method many times. And also many chemists use this spectroscopic method, spectrophotometric method. And always we need to make a standard curve. Sometimes, many times, standard curve is called calibration curve. Okay, so this problem is asking us, like, do you know how to interpret a standard curve? Okay, we'll be studying this one together. The student uses a 0.1 molarity solution of copper-2 sulfate solution to make 3 more solutions of known concentration. In order to make a standard curve, we need to prepare a solutions, different concentration with known concentration, and we will be measuring absorbance in 50.0 milliliters of milliliter volumetric flask. So as I said, the copper-2 ion is dissolved in water. This one is hydrated by water molecules, and the water and copper-2 plus this complex is absorbing visible light, showing a blue color. And let me show you a schematic representation of how to measure absorbance in a UV visible spectrophotometer. So we are preparing the sample and using pipette, transfer pipette, and put the sample into sample solution in a cuvette. And we are using, usually in the general chemistry level, we are using this plastic cuvette, but when we need really a more precise method, then we are using more expensive quartz cuvette. Quartz cuvette is very expensive one. Anyway, so in this spectrophotometer, we need to determine the analytical wavelength, and at that specific wavelength, UV visible light is irradiated upon the sample in a cuvette, and the sample absorbs certain amount of the irradiating the intensity of the light, and so the light comes out from the cuvette is light at attenuated intensity. So the spectrophotometer, the machine detects this attenuated intensity and compares the initial intensity, incoming intensity of light and attenuated intensity, and determines the absorbance. So Beer's law is used to determine concentration, and from the absorbed value, this is the equation, Beer's law, absorbance is equal to EBC. The A is representing absorbance reading from the spectrophotometer. The E, this is the Greek letter epsilon. This is the molar absorptivity of the sample. This is the constant. So let me write it here. This is a constant. At a given temperature and given pH, molar absorptivity is a concentration, and B is the length of the pathway. For a cuvette, this is the width of the cuvette, and cuvette it is 1.00 centimeters most of the times. And C is the molar concentration of the sample. So absorptivity E and pathway length B is a constant. So when we measure A, we can determine the molar concentration. That's how it is. Now let's move on to look at each problem. Calculate the volume of 0.1 molarity copper-2 sulfate solution needed to make 50 ml of 0.05 molarity copper-2 sulfate solution. So this one is typical dilution problem. So many times in chemistry, we have a stock solution, and using this stock solution has more concentrated, it is the concentration. We need to prepare a diluted solution. The equation is M1V1 equals M2V2. In my teaching career, I see students love this dilution equation, simple and easy to use. Here, M1V1 is a stock solution, more concentrated solution. M2V2 is a diluted solution. So M1 here is 0.1 molarity, V1 is unknown, we need to calculate it. M2 is 0.05 molarity, V2 is 50 milliliters of volume. So let's rearrange this dilution equation. Let's divide both sides by M1, and M1. Then M1, M1 cancels out, molarity cancels out. V1 equals V2 times M2 over M1. So 50 milliliters times 0.05 divided by 0.1. Then this is 25.0 milliliters. When you write the answer, let's finally think about, let's stop for a moment, think about number of sig figs. 50.00 has 4 sig figs. Remember that the trailing zeros are sig figs when you have a decimal point. And 0.0500 has 3 sig figs. The leading zeros are not sig figs. 0.1000, this one 4 sig figs. Again, the trailing zeros with the decimal is sig figs. So the smallest number of sig figs is 3. We need to represent final answer as 3 sig figs. 25.0 milliliters is needed. So here in the writing your answer, be careful about the trailing zeros, because we need to represent the answer as 3 sig figs, we have to write up to 25.0 mil. When you write simply 25, then even though your answer is correct, the value is same, but the concept of sig fig is missing there. So then the people, for kind of instructor like me, when grading this kind of problem, then we are maybe taking out small points off. Well, when you write 25.00 mil, then this one also has missing the concept of sig figs. So the people grading maybe take a small point off. So be careful about the sig figs when you write the answer finally. Let's move on E. Briefly describe the procedure the student should follow to make 50 ml of 0.05 molarity copper 2 sulfate solution using the stock solution. Point 1, more concentrated solution. Let me call this one stock solution. A 0.1 molarity, a 50 milliliter volumetric flask, and other standard lab equipment. Assume that all appropriate safety precautions will be taken. Okay, so volumetric flask has a narrow neck and it has only one etching mark. So this one is very precise equipment to determine the volume. So let's add 25.0 mil of the stock solution first, 0.1 molarity of this blue copper sulfate solution. Then in order to transfer, and let's use a volumetric pipette. When you have a 25.00 mil volumetric pipette, let's use this one to transfer this to the solution. Because this is critical, 25.0 mil, this one, we need to prepare this one and transfer this one. Then add deionized water to the mark. So the meniscus is heating, adding DI water, and initially we add it quickly, and as the DI water, the water level, solution level goes up, getting closer to the etched mark. So we need to be slowing down in addition of the water. And when the meniscus hits the etched mark, stop there and put a lid. Finally invert several times to mix well. So here, the last step is also, we need to consider this one. Okay, you can just add DI water to the mark. You might think this is the last step, but we need to mix this one. When you add water, then the only way they are mixed is only by diffusion. It's a very slow process. So we need to put a lid and invert several times to mix well. So add the last step, make sure. And the next one is very important problem. So as I said, for this spectrophotometric method, always, no exception, always, the scientists and chemists must prepare a standard curve. Okay, so reading this kind of curve is important student learning outcome for AP chemistry students. So I see this kind of problem, graphing, is given to the students more and more times, many times in these free response questions, number 1 and 2, I saw also many graphings. So here, this one is also important graph. Let's gain our understanding the interpretation of this standard curve. So what is shown on the x-axis is the concentration molarity. What is shown on the y-axis is absorbance, reading, the value of reading from the spectrophotometer, the solutions in the cuvette. Okay, so we have 4 data points. the data points is reference dot, and the best fit line, we call this a linear regression line, is also shown. But the problem is the equation is not given. Usually, when you plot this one, plotting the program gives us the equation of the linear plot. But this problem, free response question 3 is asking the students, do you know how to interpret, how to determine the equation of the line, this linear line? Okay. Then let's try to determine the equation of this linear regression line. First, we need to determine 2 points. Remember, for a linear line, we need to read two points, the x-axis and y-axis. The coordinate value of the 2 points. The important thing here is that the y-intercept, okay, y-intercept is 0. When I look at the data, it is extended to the 0. It is set as 0. So that's very good. Y-intercept is 0. And we need to read one more value. And the terminal value is good because it is 0.100. You can use any of the 4 data points, but for me, the last data looks good to determine the value. The x value is 0.1000 molarity. We need to determine the y value. So let's look at where, not the data points, look at the linear line, okay? Where this linear line intersect with the line, and it is clearly above 0.6. So 0.6 is certain, next number is estimate. So this value is my estimation. Because we have only 0.6 and 0.7, there is no 0.61, 0.62. So we need to estimate. So this is estimated value. Important thing is when you read the value like this one, you cannot go further than 0.6. So you cannot read it as 0.623. No, you cannot. Or 0.612. No, you cannot do that. Because already 0.62, that one is estimated value. You cannot. We need, our value should be containing only one estimated value. Only one, the last number should be an estimated value, okay? Once you determine this one, remember the equation is y equals mx plus b. B is the y-intercept. Here is 0. That's good. We need to determine the slope m. And here from this point, we determine the coordinate. Coordinate is 0.100 and 0.62. So then rise over run. You can plug in rise over run. Slope is equal to 0.62 molarity divided by 0.62. That's the y value, and divided by 0.100, and it is 6.2. This one top value has 2 sigfigs, and bottom one has 4 sigfigs. So we need to have only 2 sigfigs, 6.2. Then equation is y equals 6.2 times x. What is y? Y is absorbance. What is x? X is a concentration in molarity. So then we are ready. We already determined this concentration. So determination of this concentration, very important point. This is a key point here. I think the grading policy is giving more weight in determination of this equation than other calculations. F, the absorbance of a copper sulfate solution of unknown concentration. So we have, once we determine this standard curve, we need to determine the concentration of the solution, copper to sulfate, and we are measuring. We're using transfer pipette to transfer some of this solution into the cuvette. About 1 ml is good enough, and then measure the absorbance. The absorbance is turned out to be measured to be 0.19. Determine the molarity of solution. We already determined the linear equation and plug in 0.19 is the absorbance. This is the equation. Then 0.19 is equal to 6.2 times concentration. Let's divide both sides by 6.2. Then concentration is 0.19 divided by 6.2. This value is 0.0353 molarity. and 0.19 has 3 sig figs, 6.2 has 2 sig figs. So we need to have only 2 sig figs. 0.35, the last number is 3. So 4, 3, 2, 1. The number is less than 5, then drop it. Final answer is 0.035 molarity. Okay, so we were able to determine the concentration of this copper to sulfate solution. Let's compare this one to the previous one. So gravimetric method, we were able to determine the concentration here. This one is 0.0318 molarity. That's it determined from the gravimetric method. And our spectroscopic method, this one determined by 0.035. So they are similar. Gravimetric method is 0.0318. This is 0.035 molarity. They are similar. I think by the gravimetric method, when you do these multiple steps, when you precipitate the solution and precipitate the precipitate, and when you measure out, filter them and dry them in the oven. In the filtration, you cannot have 100% of yield. So it is unavoidable. It is kind of, we are always losing some sample in this and precipitation method. So it is end up with a smaller value of the concentration. This method is more direct. We didn't separate anything, just solution and measure out the absorbance. So we do not lose any sample. This is why I think it is more accurate method, 0.035. Okay, so a second student performed the same experiment. So we have 2 students and it is asking to compare the first and second student. There are a few drops of water in the cuvette. Before the second student adds the copper sulfate solution of the unknown concentration, will this result for the unknown that is greater or less or equal to the concentration determined in part F? Justify your answer. Remember, like we are adding about 1 ml of the solution, about 1.5 ml or 1 ml of solution to the cuvette to determine the concentration, to read the absorbance value. Now, because the water droplet is remaining in the cuvette, the water droplet will be diluting the sample. So then the absorbance level will be decreasing. As a result, the final concentration determination will be less than the value in F. Okay, so let's summarize what we learned in solving this problem. This one is asking us important lab skills. First, gravimetrically, using precipitation method and form a solid precipitate and filter them out using Buchanan funnel and dry them overnight and determine the mass. From the mass, we go step by step determine the molar concentration of the copper to sulfate solution. And second, spectroscopic method, spectrophotometric method, using a setting of a standard curve first from the known 4 samples of known concentration, and then making standard curve and determine the equation of the standard linear line, and then determine and measure the absorbance of the unknown sample, and then plugging into the equation, calculate the concentration. So this second method is more frequently used in chemistry. As I said, I have used this method many times in my research career. Okay, it is good to have this research skills, lab skills, and have understanding how to calculate, determine the concentration of unknown solutions. Thank you, everyone.